Hello everyone, and once again I welcome all of you back to the course on manufacturing methods. In the previous lectures, we have already discussed about various expandable mold processing like cell molding, then we have studied the investment casting, okay, where we have discussed that it's like a lost wax process. That means pattern is made of wax material, and all the processing steps we have discussed, and what are the advantages, limitations, etc. Those things also we have discussed. Next, we have basically discussed about the permanent mold casting. In that particular case, the normal consideration about different permanent mold casting that we have already discussed. We have seen that basically these permanent molds generally they are made of generally two halves, one being the fixed half, another being the movable half, and inside of it, whenever we join, or you can say that close both the halves with arrangements for opening and closing whatever is provided, so then inside it we get the mold cavity. And we have already discussed like how some coating is being made which facilitates easy removal of the solidified metal, etc. Those things also we have discussed. And later on we have studied about the different advantages and limitations of permanent mold casting and where it is applicable and all. So today in this particular lecture we are going to discuss about die casting, also known as pressure die casting in the Europe. So it's one of the most common type of permanent mold casting, okay. And what are the in basic terms, okay, what is basically die casting or pressure die casting? So generally the molten metal we already know. In case of metal casting we work always with the molten metal. So here the molten metal is forced into the die cavity under high pressure, and its pressure ranges from 0.7 megapascal to 700 megapascal. That's a very huge range that we have. And during the whole solidification process this particular pressure is maintained. So basically as the molten metal is forced using a high pressure, so the name itself is kind of pressure die casting or die casting. So here generally in this particular case of die casting, which is nothing but a kind of permanent type of casting process, so here the surface finish as well as the tolerance of the die cast parts are generally very good, and in most of the cases they don't require post processing operation. So this die casting molds, which also we can call as the dies, okay. So these dies are nothing but the whatever molds we talk about in case of normal casting process. So here the dies are having the cavity, okay, as it is the die casting. So we can also interchange the word mold with die here, okay. So these dies are generally expensive as they are made of very high strength metals, and generally die steel and all, and making the die itself is kind of a expensive process. That's why they are generally are expensive, and it also takes some time, okay. So in this particular case, what is the basic difference from the other type of casting is like here we use the high pressure to force the metal into the die cavity. In the other cases, whatever different types of methods we have already discussed, in most of the cases the flow of molten metal to the die cavity was due to the gravitational force, or due to the we consider inherent fluidity of the molten metal itself, and with respect to time and due to the gravitation pull, etc., it generally flows through the nook and corner of the, you can say, mold, okay. So now here in this particular case about die casting, we are going to discuss two basic types of die casting methods. One is the hot chamber die casting method, next one is the cold chamber die casting method. So now we come to the hot chamber die casting method. So now what is this hot chamber, what is this cold chamber? So basically this basically comes from this distinguishing between hot chamber and cold chamber. It basically comes from one basic thing which is there in these two processes, which distinguishes these two processes. The thing is, the basic distinguishing is in hot chamber die casting. What basically happens? There will be some arrangement in the chamber itself to melt the metal there. Okay, and after that, from there will be arrangement to, you can say, fill the molten cavity, or you can say the die cavity from the molten metal which has been produced there. But in case of your you can say cold chamber die casting, so generally this distinction is there. That means here whatever is the metal is there, so that is melted in a in a different environment, or a different environment, or you can say at a different location or different arrangement than that of the particular die setup. Okay, so now come to the hot chamber die casting. So here basically what happens, the metal is melted in a container, and there will be some piston. Okay, so a piston injects the certain volume of liquid metal under high pressure into the die cavity, and there will be a kind of in the arrangement itself you will see in the figure, it's the molten metal is thrown to the die cavity through a gooseneck portion, and there will be a nozzle. Okay, and as we are talking about pressure die casting, so here in case of hot chamber die casting, generally the pressure ranges from this 15 megapascal to 35 megapascal, and the production rate is kind of high. Okay, and these processes can be very easily automated also, so high production rate we can obtain. Okay, and as we already know, it's a kind of permanent mold casting. So once again there will be like opening and closing of two halves of the mold or the die, you can say, that will be there. Okay, and generally what happens, this hot chamber die casting, the application of this hot chamber die casting, it's generally limited to low melting point metal or alloys. And one of the we can say requirement is they should not chemically attack the plunger. Plunger is nothing but the kind of this piston which actually forces the molten metal to the die cavity and other mechanical components. Okay, it should not react with it. Okay, so that there is no erosion, or you can say different chemical like deformity etc in the whole system. Okay, otherwise all the system may fail. Okay, and why we are talking about that means it is generally limited to low melting point metals or alloys, because later on in the figure, once we discuss with respect to it, you will see that what we do, the metal is melted inside a container. Okay, melted in that particular container itself. So that's why so as to make the things less sophisticated and all. Okay, so generally whatever provision is there in the container itself. Okay, there is a limit up to which the temperature we can achieve, and if we go beyond it, basically high temperature metal if you're talking about, then the whole arrangement whatever is there, okay, right from the metal of that particular whole container, similarly the lining, the piston etc, all those other mechanical parts, they has to be kind of, we have to take extra care, and all those material also has to be kind of different. Okay, that which will be able to take that particular terminal load. Okay, so that's the whole system will become costlier also and bulkier also. That's why generally in this particular case it is limited to low melting point alloys. Okay, and generally the common casting metals which are generally cast with respect to this hot chamber die casting, zinc, tin, lead, magnesium alloys etc. Okay, metals etc. So these two figures basically discuss about our hot chamber die casting. So now what happens, so once again there will be two distinct setup. One is the this main hot chamber. Okay, where basically we will be melting that particular metal, and there will be provision for forcing the metal inside the die cavity, and the other portion is basically our that expandable die, or you can say that particular mold in our case. So now these are the two things, and generally these are joined by this particular gooseneck portion as well as the nozzle portion. Okay, so now what basically happens, so there will be, as we have said, that there will be like, as we already know in case of permanent mold casting. Okay, so in the permanent mold, okay, it has got two basic halves. Okay, here this is the fixed half, and this portion is the movable half, and once we close it through whatever the mechanism for opening and closing, here we have got the ejector pins here and here. Okay, so once we close it at that particular close timing, so this white portion, this becomes the our mold cavity, or this the whole system is acting like the die. Okay, so we have this die cavity. Okay, that means that is the shape we basically want after the whole process is over, after the casting process is over. Now in case of our hot chamber casting, so here this is the chamber we have, okay, inside it, and this is the, you can say, the portion where in that particular whole pot we will be melting the metal here itself. Okay, so there will be provision in this pot to heat it. Okay, so there may be induction heating, there may be some other types of heating also. Okay, but here basically we are getting the molten metal. So after that, what basically happens, so along with this particular whole setup, basically this gooseneck portion is there, and there is provision, or you can say the connection of this particular hole, okay, to enter the liquid metal. Okay, so that through this particular nozzle, basically molten metal can enter in the die cavity. Okay, so now first, there are two figures we are showing. Okay, first figure is with the die closed and the plunger which is withdrawn. This is the plunger. This has been withdrawn. Okay, and the molten metal now pours inside the chamber. So just like you consider like your seedings. Okay, so when it is withdrawn, that means it creates some vacuum. That is suction pressure is generated, and basically this particular chamber is filled with the molten metal. Next, figure 2 shows the plunger which forces the metal in the chamber to flow into the die. Okay, so now we apply some external pressure on the plunger. Okay, it moves downward, and while moving downward, whatever previously molten metal it was there inside the chamber, it has been forced to flow in this particular direction. And while moving in this particular direction, so it passes through this particular gooseneck portion, and through this particular nozzle it enters inside this die cavity, and it fills up this particular die cavity. And now what basically happens during the whole process, for a certain amount of time, this position of the plunger is maintained. That means this force is the pressure is maintained during the whole cooling and solidification time. Okay, that is important. We just what we don't do is we just don't push this particular molten metal inside and then uh, make it retrace back. Okay, we don't do that. Okay, rather we force that we applied move this particular plunger along with this. That means it forces the molten metal to enter inside the cavity, and we keep there. Okay, we keep that particular we maintain that particular force, and for a certain amount of time, which is required depending on what is the molten metal, okay, type of metal, and what is the shape, etc., shape, size, etc. Based on that, we maintain that particular pressure during the whole cooling and solidification process. And after that is that particular metal solidifies. Okay, we already have the suppose calculation of solidification time. From that we can obtain that particular what is the timing for which we have to maintain the pressure, etc. After that, with the help of this particular ejector mechanism, this particular movable half will move like this, and it will open. Okay, it will open, and that particular molten this solidified metal or the cast part we can take out. So this completes the whole process. So next is cold chamber die casting. So now what is the difference between this hot chamber or cold chamber? We have already discussed. So here basically what happens, the molten metal is poured into a unheated injection chamber. So that is important. So now that particular injection chamber or the setup is not heated, it is unheated injection chamber, here also known as the shot chamber. Sometimes it is being asked in which process shot chamber is used. So here in this particular case, cold chamber die process. Okay, essentially this chamber is known as the injection chamber, is known as the shot chamber. Okay, so and now this molten metal is poured into unheated injection chamber from external melting container. Okay, and then definitely once again just like the previous case, and the piston injects the metal definitely under high pressure into the die cavity. On this particular setup may be either horizontal or vertical. So this pressure, its range is once again just like the previous case, it is high pressure, but range is there 20 to 70 megapascal. Within generally that is the range of pressure in which we generally work on. Okay, and this high production, it is of high production, but generally not usually as fast as hot chamber machines. It is the high production rate is there, but not as fast as hot chamber machine. Why? Because there is a this pouring step is involved. Pouring step means what we do here, we externally melt the metal with which we want to cast it. Okay, and now in that particular chamber we have to pour the molten metal very properly. Yes or no? After that only we can think of forcing the molten metal with plunger to enter inside the mold cavity or the die cavity. Okay, but in between we definitely have to have the molten metal inside that particular container. Yes, that is the pouring step is involved. Okay, which is one of the, I can say, vital step. Okay, and like in here, as we are talking about externally melting the metal. Okay, so we can have sophisticated, you can say, arrangement for melting the metal. We can go for high temperature, etc. So casting metals, they generally includes high melting point alloys of aluminum, magnesium, copper, etc. So this is the distinction. So first thing about with respect to the whatever is the facility or arrangement available. Next is working material. Okay, casting metal. So here we go for high melting point alloys. Okay, so that is one of the advantage of cold chamber die casting, because we are melting the molten metal outside of the setup. Now if we discuss about with respect to setup, so here we are showing a horizontal type. Okay, horizontal type setup. So in the first figure what you can see, we have once again, just like the previous case, we have two halves, the movable half, the fixed half. So here this is the short chamber. Okay, this is the horizontal configuration we are talking about, and during the when both the halves are closed, so basically this is the die cavity. Okay, so that means this kind of shape we want. Now what we have, this is the ramp for, or the plunger for injecting the molten metal. Okay, so that is there. So this is the short chamber. Short chamber is not heated. Okay, so now externally we are going to heat the molten metal. Now suppose consider we already have to heat the metal and it is in molten form. Now with the help of this ladle we are going to insert, or you can say pour the molten metal inside this particular cylinder, short chamber, you can say. Okay, so now this short chamber is filled with this particular molten metal with which we want to cast. Okay, and once that is there, after that what we will do, by applying force. Okay, or you can say we are basically moving the ramp this side. Okay, and along with the ramp basically, or you can say this plunger, actually this particular molten metal will be forced to flow inside this particular molten cavity, as can be seen here in this particular figure. Okay, and it fills the whole cavity, die cavity, and the pressure will be maintained, and for certain time will be maintaining that particular pressure, and you can say during the whole cooling and solidification process will let the pressure, whatever is the pressure that is required, will maintain that particular pressure, and once that it solidifies once again, then with the help of all those ejector mechanism, where that movable half of the die will be moved, and it will be the whole mold will be open. So it is a permanent mold process. So after that we'll just take out that particular whatever is the cast part we have. Okay, and that particular mold can be reused once again. Okay, so this is basically about the cold chamber die. Next we have the centrifugal casting. So about centrifugal casting, in one of the classes we have already discussed. So generally what happens, this centrifugal casting, they are a group of casting processes in which what we do, we take the help of the centrifugal force. We generate centrifugal force somehow, and centrifugal force we consider, and consider means we take into consideration the centrifugal force, and we take the advantage of centrifugal force actually. Okay, we generally, the mold is rotated at high speed, so that centrifugal force is generated and it distributes the molten metal in the outer region of the die cavity. So generally there are two centrifugal casting is there, centrifugal casting is there, centrifuge casting is there. There are some of the subgroups. So coming to the true centrifugal casting, which we have discussed once. So here basically what happens, we'll be having a mold, yes, just like in any of the casting process, okay, with the mold, and there will be provision to rotate that particular mold at a high speed. So generally why it is used, this particular mold will have, okay, and it will be rotated at a high speed. So molten metal is first, it will be poured into the rotating mold, okay, to produce the tubular parts. Generally for uh, like for commonly made parts like pipe, tube, bushing, etc., ring, etc. So for making this kind of parts, basically this true centrifugal casting is employed, okay. uh, in some of the cases, generally what happens, initially the before pouring the molten metal inside the mold, okay, the mold may be rotating, okay, from the very beginning, and after that we are going to pour the molten metal. But sometimes it is also possible, that means in some operation mold rotation it may commence after pouring of the molten metal. That means initially we will be inserting or pouring the particular molten metal, and after that we will start rotating that particular mold, okay. And say the outside shapes of the casting, it can be round, octagonal, hexagonal, etc., okay, but the inside shape is perfectly round due to the radially symmetric force. We already know if we have this kind of mold which is rotating, so basically for rotating body having mass, okay, basically we know a centrifugal force is generated which acts in the radially opposite direction. That means if we pour something here, which is, suppose this is the mold, okay, we are talking about, suppose this mold. So whenever we uh, and this is another view, okay, so about this axis it is rotating. So whenever this particular mold is rotating and we pour some molten metal in the rotating mold, so there will be provision with the help of some drive rollers. Basically there is a provision, that means the cylindrical mold, it will be rotated. These drive rollers will have, it is in contact with them, okay, so the mold also will be rotating, okay. So now we already know, so centrifugal forces will be acting in this particular case, which is acting in the radially, it is kind of symmetric and acts radially in radially outward direction, okay. So now the outside shape of the casting can be round, octagonal, hexagonal, etc., whatever, okay, but the inside shape will be theoretically perfectly round. So depending on what kind of shape you have on the mold cavity, suppose this cavity of mold cavity is, suppose like this, okay, like this particular hexagon, okay, then if it rotates, then whatever molten metal we have, okay, so they will be forced in radially outward direction. That means this side, that side, like that, okay, and they will move and surround here, and due to the radially symmetric force, actually it will deposit like this. So here, here it will be deposited, but this side, this face will be, it is, the inside face will be kind of circular, okay, and here it will be deposited, and if sufficient time is there for cooling down, so it will solidify here, and we are going to get this kind of casting, yes. So depending on whatever is the shape, so this outside shape may be whatever, okay, but inside shape this will be kind of round due to the radially symmetric forces. So there may be two positioning of this particular mold, okay, it may be vertical also, and then it may be rotated, okay, or it may be just like in this particular figure, it may be horizontal also, okay. So there is generally this horizontal configuration is more preferred over this particular vertical one. It is not that much, it is used, but it is not that much preferred. Why? Because in case of vertical case, okay, we already know, even though it is rotating and centrifugal force will be like this, okay, and suppose the tubular parts will be something like this, Okay, it will be uh, it will move in this particular phase, and it will be forced in this particular direction and solidify here. But we already know if you're talking about molten metal and all, okay, it has got certain mass associated with it. That means some weight, or you can say gravitational pull is there. So even though theoretically it should solidify like this, okay, but what basically will happen is, due to the acting of the gravitational force, so this side, this lower side, okay, will be kind of bulkier, and here it will be kind of leaner. Okay, so that means in this particular phase, suppose this way we want it, okay, but what will happen is it will be something like this side, lower side will be somewhat distorted, and here deposition of material will be more. Okay, this is this side. Okay, so I hope you have understood. So already this rotational speed or true horizontal centrifugal force. Okay, for that we already know centrifugal force, it can be given by mv square by r. So there is a factor known as the z factor or zf. It is not your girlfriend and all. Okay, so z factor, it is the ratio of centrifugal force to the width. Okay, so from here gf can have v square by rg. Okay, because we already know velocity v equal by dn by 60 we can write. So from this particular z factor value, if we simplify, then we obtain an expression like this. Okay, where n is the rotational speed of that particular mode. Okay, so it is 30 by pi root over 2z. This zf is not two different z and f. It is, you can also use like z suffix f. Okay, that is up to you. Okay, so zf and divided by d. But what you must remember is what is this particular d. So d is the inside diameter of the mold. Okay, inside diameter of the mold. Okay, don't make it you can say like don't make it outside diameter, or don't constitute it the inside or outside diameter of the cast. So it is inside diameter of the mold. Okay, now if the z factor is too low in case of centrifugal casting, the liquid metal will not remain forced against the mold wall during the upper half of the circular path, but it will fall inside the cavity. So it is something like, it does, maybe all of you have already seen the in circus etc., in some you can say in some sphere or ball kind of fence. Okay, some bikers, they tend to like suppose this biker is here. Okay, they move like this. Okay, and here also they move safely. Okay, so there is a safe speed. I feel all of you have solved this kind of problem. So if that is there, so they can safely move like this. Okay, similar is the case in case of our centrifugal case, somewhat similar. Okay, so this z factor is nothing but that z force we are talking about. Okay, that it is associated with the gravitational pull. Okay, which is on in terms associated with the centrifugal force which is there. Okay, so now if we are talking about this part, if z factor is too low, okay, then for the upper half of the circular part, so suppose this way due to the uh, suppose this way due to the centrifugal force we have obtained this particular casting. So if it is too low, then from this portion there will be tendency of the material to fall, okay, to rain inside the cavity. So we have to be sure about, we have to be cautious about this z factor and all. Okay, and generally for in case of horizontal centrifugal casting, z factor of 60 to 80 is found to be appropriate. So if it is safe, that means okay, there will not be any tendency of this particular upper portion to fall due to you can say due to the associated gravitational pull, etc. So we have another version, so that is semi-centrifugal casting. So here also it also uses centrifugal force. Okay, but the difference is here we are going to obtain some solid casting rather than tubular parts. In the true centrifugal casting, we generally use it for producing tubular parts. Okay, so generally in this particular case, molder designed with risers at the center to supply the feed metal. So here see, generally two symmetric hubs are there. Okay, once again it is centrifugal, it is rotated, so once again this you can say centrifugal force will be generated. So inside it already two parts already, you know, cope and drag portion. Okay, so now the casting is already there in the blue part. Okay, so this way the riser will be there, and due to the centrifugal force, so this side, that side, everywhere radially it will be metal will be distributed. And as the riser is inside, so it is going to compensate for all the shrinkages and all, and this part also is going to be filled up. But due to the centrifugal force, what basically happens, the density of the metal in the final casting, it is greater in the outer section, this way, this side, that side. Okay, because this F is always working, centrifugal force is always acting in the radially outer zone. Okay, so metal will be more deposited at the wall section. Okay, so and but in this particular, this is this portion, this is this portion. Okay, so but in the mid, okay, in the central zone it will be less thickened. Okay, less density. So generally what happens, often it is often is for parts in which the center of the casting is generally machined away. Okay, and it eliminates the portion where quality is lowest, because density is very less in the center. Okay, in the center portion. Examples like the wheels, pulleys, etc., where we don't have this particular portion, it is not required, it will be later on machined away. So this other portion, external portion, it is already in a better position. Okay, and here also we can use expandable molds. Similarly, we have centrifuge casting. So it is just like in the case of centrifuge, you might have already heard in the medical terminology also. So here basically what happens, mold is designed with part cavities which are located away from the axis of rotation, so that molten metal which is poured into the mold is distributed to this cavity by the centrifugal force. Okay, so you can have a number of this kind of we can have number of this kind of uh, a number of this kind of cavities. Okay, and generally it is used for smaller parts, the centrifugal car. Okay, and here it is not necessary that it has to be radially symmetric only. Okay, in other centrifugal casting it is required that it is, has to be radially symmetric, parts has to be radially symmetric. So it is in a particular this kind of you can say plate also, there may be a number of, you can say this kind of mold cavities. Okay, and from the meat we can pour the particular molten metal, and due to the centrifugal force it will be distributed to the all those uh, cavities which are at a distance from the center. Okay, so centrifugal force will be once again be there. Okay, so this kind of this like shape we may have. Okay, this is the, we can have the sprue kind of thing. Sprue means just like in the case of investing casting, if you recall. Okay, sprue, it's like one in a single case, that means multiple number of molds are there. Okay, so this is the distinction. So we also have like in the process industries, we have continuous casting. So what is this continuous casting? That means continuously from the molten metal itself to the final whatever is the shape of that particular cast part that is required. So continuously in the step by step, in the long run the whole process is over. So that kind of casting is known as generally continuous casting. Generally whatever like the all those feed bar stocks, those village bloom, etc., of different mild steel or whatever this cast iron, etc., are generally made. Those are generally made in the industries, in the industries in by continuous casting processes. So they are generally usually employed in the solidification of basic, having constant cross-sectional stress that becomes feedstock for deformation process like rolling and forging. So in the next modules we'll be discussing about this rolling process, forging process, etc. But whatever feedstock we generally use in the rolling process, forging process, etc., okay, that is the bar billets, those bloom billets, etc., those are produced by this kind of continuous casting. So what basically happens, at the top basically we have the ladle with molten metal. Okay, and then with the help of this turn this, okay, we like basically will be having the continuous cross section mold, okay, and continuously like molten metal will be flown through here, okay, and there will be a long conveyor belt and all, okay, that kind of arrangement, and through this actually it will move, and during that there will be water spray for cooling purpose, water spray heater etc will be there, okay, and guiding roll, all those setup will be there, okay, and once it moves in this particular direction, okay, it will be progressively solidified also, and progressively we are going to get whatever is the shape required, then we'll be having all those pitch rollers etc so as to guide it, and we'll be having the bending caster etc, then if required whatever is the direction etc that will be required, okay, and you can see like this, okay, so from here to here once again spraying of molten metal, water jet etc, water heating, water cooling, uh, air cooling etc, it will happen, and it should be straight in here, then we can have the bending and etc, and we can have the final shape once it goes out here, okay, we have a continuously the final shape is given, and continuous in a continuous way we can have this particular whatever is the final product, and generally these final products which are in the form of bloom billet etc they becomes the feedstock for feedstock, that means the raw material for the deformation process like rolling, forging etc, because we already know for any process generally in the nature whatever is the raw material it is generally not available in the exact size shape etc which are required in case of rolling, forging etc, but from somewhere from certain feedstock we have to work, and these feedstocks are generally continuously cast in this continuous casting process, okay, so I hope all of you have understood. So in the next classes we'll be discussing about the casting qualities and casting quality, how to do the inspection etc, what are the different problems associated, so those things we'll be discussing in the next class. So thank you.